Today we were talking about how doing the limit of the sum is really just the same thing as the integral. And if we write it as an integral, it is way faster because that just means the antiderivative, and we can evaluate those and get a number answer by doing the antiderivative of the top limit minus the antiderivative of the bottom limit. Remember, if we have a definite integral where we have those top and bottom limits, then we don't have to have a plus c on the end because it would cancel out. If, however, we did not have numbers to plug in, you would still need to put your plus c on the antiderivative. So let's say I asked you to evaluate this on the interval 0 to 1. We could, do the whole summation rules and the limit and all of that. But we also now know a little bit about the limit of the sum. We know the limit of the sum is really the same thing as an integral. What are my limits from where to where? Okay. So now I just need to rewrite this. Remember, when we used to create that, we had to find our change in x and our x sub I, right? Change in x was ending minus beginning over n. So my change in x is 1 over n. X sub I is your starting point plus 1 over n times I, which gives us 1 over n. Okay, so let's think about 2 times I over n squared. Okay, 1 over n I, isn't that the same thing as I over n? So if I took out my 2, I over n squared, could you write that as I over n times 1 over n? Is this the same? So we have 2. I over n is our x sub I, which would have been an x in the original function. 1 over n is the change in x, which when we have an integral, that becomes the dx. So the original problem was just the integral from 0 to 1 of 2x dx. Can we do the antiderivative of that? What's the antiderivative of 2x? 0 to 1. And we get 1. I would really like to add in an extra problem here, if that's okay. So what if I asked you to evaluate All right. How is this one different than the previous one? It doesn't have the sum part, does it? So our goal in these problems is to see if we can write them as integrals so that we can quickly evaluate them. Could I write this with the sum? Probably. Let's see. So what is the change in x going to be? Yep. Change in x is our 1 over n. And then our x sub I is the starting point plus the change in x times I. So that's I over n. Same thing because we're still doing 0 to 1. Alright, so if I asked you to use this to rewrite that sum, still have our limit. And we'd be adding up from 1 to n. Alright, so now we figure out what we would do here. If I need to rewrite this, the 3 on the bottom, could I just kind of pull that out and make it a 1/3 in front? And then you have like 1 to the 5th, plus 2 to the 5th, plus 3 to the 5th. Okay, what if I kept 5 of the n's here and pulled the extra one out? Then I have a 1/3. This is the sum of I over n to what power? The 5th times my 1 over n. Okay, but really I want to write this as an integral. So this would be the integral. Where are we starting and stopping our interval? 0 to 1. 1/3. I over n was what? I over n is the x sub I, so it's just x to the 5th. And 1 over n is a change in x, which with an integral we write that as dx. So we took some ugly summation problem. First we wrote it with a sum, so that then we could replace the limit and the sum with our integral. Right, so the antiderivative of x to the 5th would be x to the 6th. That means you need a 1/6 in front. So 1/6 times 1/3 is 1/18. Any questions on that? Okay. So a few more things about our integrals. We have some properties. The first one, I don't really find it useful. It's not like we really need to remember it because we can do the antiderivative of a constant, right? We just throw the x with it, and then when you evaluate, your x gets replaced with the top minus the bottom. So not overly important. The second rule is somewhat helpful. If you have a coefficient, we know we can pull it out in front of the integral, so it just gives us something nicer to work with. We don't have to carry that coefficient all the way through. The last one is probably the most useful. If you have the integral of things being added together, you can break them apart. So you can take one integral and break it apart and add them together. And it would also work with subtracting. So we can break apart terms, integrate those separately, and then combine our answers at the end. We can also break apart an integral with some point in the middle. So if, let's say, I had a function like this, okay, let's say this is my A, and this is my B. If I want to integrate from A to B, you could break it into pieces and maybe integrate from A to C, and then integrate from C to B, and put those together. This is going to be useful if you think about like absolute values. Anytime we have an absolute value when we were doing derivatives or anything, we had to rewrite it without the absolute value symbol, and our breaking point was the middle. With this, you have to be very careful. If we have an absolute value, if you don't break them into pieces and add them together, then if you just took away your absolute values, positives would be positives, anything below the axis would become a negative, and you would get an overall change of 0. So we do have to rewrite absolute values. And that's what we're going to try next. So if I looked at this, I cannot take a derivative with an absolute value. I can't do an antiderivative with an absolute value. So I have to rewrite this. We are going to break apart our intervals. So this one will have to start at -1. And this one will end at 3. But we need some point in between -1 and 3 to break them up. And that comes from what makes the inside of our absolute value equal 0, which in this case is just 0. Now, if it were like an x minus 1 inside my absolute value, then my breaking point would be at 1. It's whatever makes the inside of the absolute value 0. All right, so now we think, if we put in things between -1 and 0, then like if I did -1, the absolute value of -1 is +1. So our equation becomes the opposite of that. The absolute value would make it positive, so it's the opposite. So I want to integrate a -2x. And you have to have the dx with every interval. Okay, so that we are rewriting this so the absolute value isn't needed. If I put in a -1 up here, I would end up with 2 times 1, which is 2. If I don't have my negative, then if I put in a -1 down here, I get -2. Those are not the same. I need the opposite of that negative to make it a positive. If you're plugging in things between 0 and 3, does the absolute value change them? No, so that is just the normal function. Right, this is the hardest part, rewriting it. Are there any questions on what I did here? So now we can integrate. What's the antiderivative of -2x? That's squared. I'm going to move that one from -1 to 0. What is the antiderivative of +2x? X squared. I'm going to move that from 0 to 3.
So why was that 2x positive again?
Because the absolute value didn't change it. So if we think about like the definition of absolute value, you get the same thing you put in if you put in a positive. You get the opposite of what you put in if you put in a negative.
Okay.
So since these numbers, my limits were positive, the absolute value didn't change it.
Okay.
Other questions? Look at this. The opposite of 0 squared is 0 minus the opposite of -1 squared. So I get 0 minus negative, so +1. And put a 10. Questions on that? I think I've got another absolute value one, but I think I may add in a different one before we do that next one. I don't know if you have room on the back page, maybe. So I'm going to add in an example. Let's say I asked you to integrate from -3 to +4 of the absolute value of x plus 2. Okay, so first we have to write this without an absolute value. We're going to have to break it into 2 different intervals. First one starts at -3. The last one will have to end at my 4. To find out the breaking point, you have to say what makes the inside equal 0. What is it? So we'll go from -3 to -2, and from -2 to 4. Alright, if I am plugging in -3 to -2, so if I put in a -3, do Do you get a positive or a negative inside the absolute value? A negative. And the absolute value would make it positive. So it's the opposite of what I'm putting in. But if you put in something between -2 and 4, do you get a positive or negative inside the absolute value? Positive. So does the absolute value change it at all? No. So in that case, we can just drop. So from here we have different options for working it. If you want, you're welcome to pull out your coefficient. That was one of our properties. So if you wanted to take out your -3 and then just integrate x plus 2, you're welcome to. That's when we take out the +3. What's the antiderivative of x plus 2? Same antiderivative here. So then we have to evaluate that. So if you put in a 2, 4 times that is 2 plus 4 minus, if you put in -3. That's just so we put in a 4, 16 times. And what do we get? And again, is it okay to have positive answers on integrals? Yeah, and you know, this first integral turned out to be negative. That just meant that part was below the axis. Questions for me on that? All right, so we are going to do one last example for today. The comparison property at the end of this section is actually considered an optional topic, so I am not going to include that. It's basically just talking about if you have integrals that you can't calculate, but you know that graph falls in between two things, you can do the two you know. It's kind of like the squeeze theorem for integrals. So it's considered optional, so we are actually going to skip that. But I do want to do one more absolute value one. The integral from 0 to 2 pi. Cosine, the absolute value of cosine x minus sine x. Okay, so our breaking point has to be when the inside equals 0, which is when cosine is equal to sine. If sine and cosine are the same, that means they're either both positives or both negatives, right? In which quadrants are they both positive? 1. In which quadrant are they both negative? 3. So we're going to get 2 answers. Reference angle. When are sine and cosine the same? It's 45 degrees in radians. That would be pi over 4. Okay. So pi over 4 in quadrant 1 is pi over 4. So we'll do 0 to pi over 4. We'll have to go pi over 4. Pi over 4 in quadrant 3 is 3 pi over 4. And we'll go from 3 pi over 4 to 2 pi. So because these are equal multiple times, we have to have multiple integrals. Alright, so it starts out between 0 and pi over 4. We basically need to know, is this positive or negative? Okay, there's different ways of doing it. You could plug in a number. Pi over 4 is 45, right? So something between 0 and 45, maybe 30 degrees. What's the cosine of 30? Cosine would be radical 3 over 2. What would be the sine of 30? So when you subtract those, would you get a positive or a negative? Positive. Radical 3 is bigger than 1. So the absolute value is not changing. If you don't like that, you could also think about the graphs. We know sine looks like this. We know cosine looks like this. So we know that cosine starts out on top, right? So cosine minus sine would have been positive. Okay, between pi over 4 and 3 pi over 4. So if you're looking at the graph, here's pi over 4, here's at 3 pi over 4. Which one's on top? Sine. So cosine minus sine is negative. The absolute value would make it positive. It would flip it. So you could put a negative in front. Would it confuse you too much if I just wrote it as sine minus cosine? That's the same as negative cosine plus sine. If you didn't want to do it that way, you can plug in points. You just have to have something between pi over 4 and 3 pi over 4. So maybe like pi over 2. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. So we see that sine is there. Alright, after that, from 3 pi over 4 to 2 pi, which one's on top? Cosine. So cosine minus sine would be positive. So the absolute value doesn't change. Alright, so a lot of work in writing this step. We had to figure out where they met, and then we had to rewrite it without our absolute values. Do you guys have questions right there? So now, let's go through. So what is the antiderivative of cosine? Minus. What is the antiderivative of sine? Did we do these right, guys? The antiderivative of cosine is positive sine. It's when saying what has a derivative of cosine. Derivative of sine is cosine. Now the antiderivative of sine would be negative cosine. And you can check it. Derivative of sine is cosine. Derivative of cosine is negative sine. Right. So here, antiderivative of sine is negative cosine minus the antiderivative of cosine is sine. Okay, antiderivative of cosine is sine minus the antiderivative of sine makes it a negative cosine. So, what is the antiderivative, or sorry, now we're plugging in. What's sine of pi over 4? Plus cosine of pi over 4 is minus Now we put in the 0. Sine of 0 is 0. Cosine of 0 is 1. So this is representing that one. Now we do the next one. So cosine of 3 pi over 4. So that's in quadrant 2. Cosine is negative in quadrant 2. So 2 negatives would make a positive. And it's the same as cosine of 45, so radical 2 over 2. Minus we have a mistake. You guys haven't caught it?
Mm-mm.
We said quadrant 3, but then I wrote down 3 pi over 4, and 3 pi over 4 is in quadrant 2. That should be a 5 pi over 4. It's an easy fix. Sorry about that. You guys were supposed to tell me I messed up. Okay. So now right here in quadrant 3, sine is also negative. So minus negative makes plus. The sine of pi over 4 is radical 2 over 2. Okay, minus cosine of pi over 4 is radical 2 over 2, and it was a negative. Minus radical 2 over 2. All right, so there's that piece. One more. So if we do this one, we have to start out with 2 pi. That's the same as 0, right? Sine of 0 is 0. Cosine of 0 is 1. Okay, 5 pi over 4, we already said sine was negative radical 2 over 2. And cosine is negative radical 2 over 2. So if we evaluate all this, we get radical 2 minus 1 plus radical 2 minus a negative, so plus radical 2 plus 1 plus radical 2. 1's cancel and we get 4 radical 2. Alright, definitely kind of ugly on that one, but good refresher with all of our trig. That is our stopping point, so you have the rest of the hour to work on that handout from